Okay, in these two slides I'm going to continue the discussion of modulation bandwidth, and I'm going to start off by giving a diagram that shows essentially our fiber optic system again from end to end, and I'm going to first of all distinguish between an 3 dB bandwidth measured in the electrical domain versus measured in the optical domain. In the last set of slides I started off by showing the input and the output of the system, and I'm looking at the optical domain. I'm looking at optical, an optically modulated signal, or a modulated optical carrier. And now I'm going to ask a more general question. I'm going to start off with an electrical signal. I'm going to use that as an input to a transmitter, and then I'm going to get an optical signal. And that's going to go through the channel, or the system, in the last diagram. And then I'm going to get another optical signal that goes into the receiver, and finally is turned into an electrical signal. Okay? And so we have several different questions we can ask ourselves. We can look at this input optical power, and we can ask ourselves, okay, given that input optical power that's been modulated at a frequency f, what is the output optical power as a function of frequency? And that's what we just answered, that question. But we can also then ask the same thing over here on the electrical side. Now we have an electrical power going in, and we have an output electrical power, which depends on the frequency. So this is characteristic of almost any system. When you put an electrical signal in, you'll get an electrical signal out, and very often a band-limited system has a decreasing output amplitude or output power as a function of frequency. And so what we've done so far then is calculated the optical 3 dB. We've dealt so far with this f3 dB as an optical 3 dB bandwidth. Okay, so we have we can say that this distinction gives us our optical 3 dB bandwidth, whereas this one is going to give us an electrical 3 dB bandwidth. And we can distinguish between those two. And basically what we're going to find at the end of the derivation is that the electrical 3 dB, the loss on the electrical side is twice the loss on the optical side. Okay, and so so we're going to be interested in general in calculating the electrical 3 dB bandwidth from the optical, converting between optical and electrical bandwidths. There's another type of conversion though that I'll show you here. We also may want to convert between the optical 3 dB bandwidth and say the optical 1.5 dB bandwidth or the optical 10 dB bandwidth. And we can define those as follows. So optical versus electrical bandwidth is what we've got here. Now I'm going to talk about optical bandwidth calculations and show you that this equation we derived in the previous video, f3 dB, f dB, this is the frequency dependent loss measured in decibels, is 3.01 times f over f3 dB squared. Okay, so this is the equation that we derived in the previous one, and this allows us easy conversion between various quantities. F3 3 dB, F 1.5 dB, F 10 dB, whatever we want. We can characterize our system by asking ourselves at what frequency is the output 3 dB below the input. At what frequency does the output go to be 1.5 dB below the output or 10 dB below the output? So for example, by definition, the loss, the frequency dependent loss in dB evaluated at f1.5 dB is equal to 1.5 dB. That is the definition. So when I evaluate the loss in decibels at that frequency, that's how much loss I've got. Okay, but this equation then allows us easy conversion amongst those. But then we can write that 1.5 is equal to 3 times F 3 dB over F 1.5. 1.5 is equal to 3 times F 1.5 dB all over F 3 dB. And this immediately gives us that F 1.5 dB is equal to 1 over the root of 2 F 3 dB. Okay, and these are optical bandwidths. Okay, so now that we've distinguished between optical and electrical bandwidth values, we like to go ahead and put, sometimes we put it as a subscript, sometimes we put it as a superscript, but we're going to call these things optical bandwidths to distinguish. Next, I'm going to show you the connection between the optical and electrical bandwidths based upon a simple photodetector circuit. Okay. First of all, though, I'm going to write that the optical power measured in dB can be written as the optical power in dB at zero frequency minus the frequency dependent loss in dB evaluated at frequency f. So this is a general equation that just illustrates by the definition this frequency dependent loss and puts any optical power in terms of the zero frequency optical power minus that loss. So this is essentially the definition of this frequency dependent loss term here in the previous slide. Okay, now what we're going to do is we're going to say, okay, let's look at our photodetector. Our photodetector has this symbol, and we're going to go ahead and draw a little circle around that. So there's my photodetector, and it's going to have a linear response. We saw these basic equations in chapter 1. We're going to write I is equal to rho times P optical. And so this is the photocurrent output. This is the responsivity, and it's assumed to be a constant in this linear model. And this is the input optical power. And so we're going to use this simple model, and what we're going to do is we're going to go ahead and put our photodetector into a circuit where we've got a load resistor now. So we have to do something with this photocurrent, and what we're going to do is we're going to drive it across a load resistor so we get a voltage output and we can use it. And so now what we can write is that the electric power is I squared R. and I'm going to write the load resistor here. So this is the photocurrent squared times the load resistor. And I can in turn write this as RL rho squared P optical squared. I'm going to finish the derivation over on the other side here. And so what we're going to do now is we're going to break this out as the same way we did with this up here, as a frequency dependent part. Now here I'm dealing with linear variables. Up here I've got decibels. I'm working in linear variables now, where I'm going to write P electric as a function of F is RL rho P optical squared as a function of F. Okay? And I'm going to go ahead and write the optical power as the product of the optical power at zero frequency times the linear loss. So instead of having a decibel value minus a decibel loss, I'm going to have a linear value times that loss value. And that comes out to be rho. And now I'm going to write P opt at zero frequency squared. And now I'm going to rewrite this term, this loss, in linear units. What is the frequency dependent loss in linear units? Well, it's the decimal frequency dependent loss. Well, I take 10 and I raise that to the minus L opt in decibels divided by 10. So let me rewrite that line there. RL rho P optical squared at 0 times 10 raised to the minus L opt in decibel units over 10, and I'm squaring that because I'm squaring that optical power. So this is just the loss ratio. So I've taken this loss in decimals and converted it into a loss ratio. When it's a loss ratio, I multiply it. And I'm going to identify this part as P electric at frequency 0. And I'm going to go ahead and plug in and I'm going to go ahead then and rewrite this as RL rho. Now I'm going to write this as P elect frequency 0 times 10 to the minus 2L optical over 10 in dB. Okay? But by definition, my electrical loss in dB as a frequency dependent quantity is minus 10 log P electrical as a function of frequency over P electrical at 0 frequency. So I have an electrical power at 0 frequency, I have an electrical power at frequency F, and when I convert that into decibel units, that is the decibel loss, frequency dependent loss part. And so we can look at this equation and we can look at these two equations and we can see immediately, we can identify that the electrical dB loss as a function of frequency is simply twice the optical dB loss as a function of frequency. And where does that 2 come from? That 2 comes from the fact that I've squared the optical power times the responsivity to get the output current. It comes from the square of the photocurrent, essentially. So you can see, I hope you can see that these two equations allow us to make this identification. Okay, thanks.